Good morning, now ladies, just gentlemen. Warm welcome from my side. My name is Patrick Stern from IBM Papst Mulfingen, and today I would like to show you one of our latest developments in axial fan technology. And I would like to show you the possibilities for improvements regarding efficiency, mainly efficiency, but also to do with noise, as you will see at the end. So this is my agenda for today. So a warm welcome, good morning. I would like to talk to you about what is a fan system, then what means fan efficiency actually, what's behind, what is an axial fan, by the way, just a short explanation. Then I would like to show you the opportunities for improvement, then the improvements itself, what we have done in the past years, so to say. Then, of course, what are the effects of these improvements with respect to efficiency, with respect to noise and things like that. And we will have a look at the so-called extended system, because not only the fan itself is important when it comes to efficiency, also the system around, so the application, condenser, unit cooler, whatever. And last but not least, I'll come with some conclusions. So let's start. What is a fan system? A fan system, how we see it, it's not just the impeller, it's the motor in case of an EC motor, and I talk here about EC technology, means electronically commutated motor. So we have got the motor, we have got the drive, the electronics, the commutation electronics. Here we have got the axial fan impeller, but also the guard, the finger guard, and the nozzle or wall ring, or however you call it, tube, belongs to the fan system. And as you can see here from these figures, the efficiency, the eta of the total system, is the product of the efficiency of each single component. This is important to know. Right, next one. What is efficiency? What's the efficiency of a fan? If you look at this in more detail, you will see that we have two possibilities to look at the efficiency. Firstly, we have the so-called overall efficiency eta E. This consists of the fan air power, the total air power, and divided by the electrical input power. And we have the so-called overall static efficiency, eta ES. And this is actually what we talk about when we talk about fans. And here we just look at the fan static air power, because the static pressure and the static air power is this figure, this value, which can be used actually in the application, like a condenser, like an evaporator and things like that. So, and this is important to know. So on the other way, it means that we talk about static fan pressure, PFS, because we talk about static air power, PUS. And interestingly, but it's logical, when we look at the same fan, the air power will always be higher than the static air power. That's logical. And therefore, the static efficiency will always lower than the total efficiency of a fan. This is important to know, because all the dynamic proportion, the dynamic pressure, dynamic power, is a kind of a loss of a fan, because it cannot be used in a normal application like a condenser, like an evaporator, like a heat pump or whatever. And so dynamic pressure is a loss, means lost energy. Right. So what is an axial fan actually? An axial fan, according to the ISO standard 13349, is an axial flow fan, and a fan in which the air enters and leaves the impeller along essentially cylindrical surfaces coaxial with the fan. Sounds a little bit tricky and complex. It means actually the air goes in an axial direction and the air goes out in an axial direction. That's it, more or less, in a nutshell. Right, that's all to mention here. Maybe one thing, this is the principle of an axial fan. So we have got here the motor in the middle, we have got here the blade, we have got here the finger guard, and we have got the tube or the wall ring or the nozzle. According to the standard, the stationary element or the stator is not part of the motor. It's actually the wall wing because it's the stationary part of a fan. It's a bit tricky, but that's the explanation according to this ISO standard, just by the way. So what opportunities do we have actually on a fan to improve the efficiency? So firstly, we have a look at the motor, at the EC motor. If you look at the EC motor itself, we see that nowadays we have already an efficiency of up to 94%. So there's not much left to improve something. Unless we use, for example, these so-called rare earth metals. But this is very expensive, and this has an impact also to the environment, which we do not want, by the way. Looking at the drive, at the electronics, we see also a similar level, which goes up to, let's say, 96% of efficiency. Also here, we have not that much left to improve anything. So what can we do? As easy as that. So we have the electronics. As you can see, 100% efficiency would be the ideal world. Nowadays, we are very close to it, so not much left. Similar with the motor, but if we look at the aerodynamics, and this is not only the impeller, it's all the other aerodynamic components, the wall ring, the guard, any straighteners, any diffusers, we will come to that point later. Here we have got the greatest potential to improve. And this is where we have worked on when we have developed this new AxiEco system. And this is still the point of interest, so to say, when we are developing new fans. Because here we still have a significant potential to improve, and not only the efficiency. And this is the interesting point. If you improve the efficiency of a fan, you improve at the same time normally also the noise behavior of a fan. So, how can we manage this to improve the fan? Firstly, we have to look at the impeller itself. So you see here a standard, let's say a standard impeller from a side view. So we have here the hub, which goes to the motor. We have several blades on this hub. We have a certain angle of this blade. We have a certain profile of this blade, and we have a certain angle how the blade is attached or attacked to the hub. And the target needs to be to reduce the friction, the air friction, which goes along the blade, which is caused by the blades, and also to reduce the turbulences which are caused by the blade itself. That's a physical effect, and this is actually, these are the areas of improvement we have here. So what else can we do on the aerodynamic system? So let's have a deeper look into the impeller. Typically the flow, the pressure characteristic, and the losses, and also the acoustics are mainly influenced by the number of blades of an axial fan, by the width and the shape of the blade, whether it has a certain profile or something. The blade angle has an influence to these values, and also the angle of attack, as I've explained before. And on this picture, you see a picture out of this is a computational fluid dynamics, so-called CFD simulation, what we are doing nowadays for a couple of years already. And we can see here, for example, critical zones signed in red, for example, where we have high velocity, and we have these blue zones where we have typically low velocity, low air velocity, and so low turbulence, low losses. And this is actually the target to have a picture that shows just blue or maybe green colors, but not red. What else do we need to consider? We need to consider also the wall ring. As I said, the wall ring is the so-called stationary element of the fan, or the stator. The task is mainly to guide the air towards the fan, through the fan, and from the impeller away. So what you see here in this picture is a cross section. So we have got here the nozzle or the wall ring. Here we have got the motor sitting in the middle, and here we have got the blade of the fan. So the air goes that direction towards the fan, goes through the fan, and leaves the fan in that direction. What can we do on the wall ring? If you look at this area here, the inlet area or the sucking area, we can do, for example, this is not just a simple radius. It's a combination of different radii in order to have a smooth or more or less a laminar airflow towards the impeller. And this can only be reached by not just having one radius, but having a constant or a combination of multiple radii to minimize turbulences in that area. So this is the main thing of a wall ring and the main task. So the radius, but also the length of the tube has an influence to the efficiency of the fan, but also to the noise, of course. What else is interesting? Also, the interaction between the blade and the wall ring is important. And this has got also a significant influence to the efficiency of a fan. As you can see here on this picture, here again we have a cross section. So this is the outer part, the tip part, so to say, of the blade as a cross section. Here we have got the tube or the wall ring or the nozzle. So the air goes in that direction and leaves in this direction. And what the effect here is, we have a low pressure area here in that area, and we have a high pressure area here. And that means, as we have a certain tip clearance, a certain gap here between the tip, the blade tip and the wall ring, this pressure difference tries to drive the air somehow backwards to the fan. And this backwards flow in that area, in that tip clearance area, causes turbulences, it causes losses, air losses, and it causes noise. As you can see here, we have partially very high velocities and high pressure differences. And this is actually one point that's very important. And what we can do here to improve this, for example, we can try to make the tip clearance smaller and smaller and smaller, but there's a certain practical limit, so to say, because this has to do with tolerances of the impeller. This has to do with tolerances of the wall ring. So it cannot be zero. It's just not possible. But what we can do, we can bring these two components together as one part. And this is what I'm going to show you on the next slide, or maybe on one of the next slides. What is also important to know when it comes to efficiency of the fan, again, we see dynamic pressure as a loss. What you see here on this slide, this is a typical air performance curve or characteristic curve of an axial fan. Here we have got the pressure, which is generated by the fan. Here we have got the air flow. And here we've got actually the characteristic, the curve. And when the fan is installed in a typical application, like you see here on this picture, a typical condenser unit, then we get a certain duty point here. The pressure which is caught, which is generated by the fan, especially the static pressure, is that pressure which can be used, because this static pressure tries to get the air through the heat exchanger. And only this static pressure can be used of a fan. But as we have learned before, we do not have only static pressure. We have a certain velocity when the air comes out of the fan. So we have a certain dynamic pressure proportion. But this dynamic pressure cannot be used. It's lost energy. And therefore, we try to keep the air velocity as low as possible and keep the static pressure as high as possible. And by this, we can improve the efficiency of a fan. So, what have we done in the past, or especially with this new development called AxiEco axial fan? The target to improve the impeller, or with a new impeller development, is always, of course, firstly, to reach the desired characteristic. because you can have a steep air performance curve, you can have a flat air performance curve, depending on your application, depending on for which application you would like to use this fan. Then, of course, we would like to minimize the drag or the friction of the blade. This can be done by a certain profile, for example. Then, of course, we need to minimize the turbulences across the blade. This is a physical effect, and by these measurements and by CFD simulation, we are trying always to reduce these turbulences. And then we need also to minimize the turbulence caused by the blade itself. So we have not only turbulences caused by the air when it streams over the blade, also the blade itself, because we have a certain edge here. We have the edge on that side, we have the edge on the other side. So, and this causes turbulences. And by a certain profile of the fan, we can reduce these turbulences. And by this we increase the efficiency and we reduce the noise. So, coming back to the tip clearance. This is actually what we have done, as I've explained before. What you see here in this picture, this is a cross-section of our AxiEco fan, axial fan. So you see here the motor, you see here the hub of the impeller. This is the blade, this is another blade. And what we have done, we have brought the wall ring, the nozzle, together with the blade. So it's one part. And by this, we do not have any longer any tip clearance. So we have no losses here in that tip clearance, and we have no noise issues. Then we have here the nozzle. We still need a nozzle, of course, but in that case, this nozzle immerses into the wall ring or immerses into the impeller of this fan. Furthermore, what we can do is using a diffuser. A diffuser increases the outlet area of the fan, and by increasing the outlet area means we reduce the velocity of the fan because the airflow is still the same. And by reducing the velocity, we increase the static pressure. And by this, we increase the efficiency of the fan. And at the same time, we increase also, or we improve the noise behavior. And this is actually what we have done also on the AxiEco. So it's not just a simple wall ring, it's a conus. And this acts like a diffuser because we have a larger air outlet area compared to the air inlet area. And this acts like a diffuser. What else can we do? We can use so-called guide vanes or straighteners. It has a similar effect. By this guide vane, or if you look at the airstream of an axial fan, especially the air outlet stream, you do not have really laminar flow. We have also some rotational proportion of the airstream caused by the rotating impeller. And this rotational or this swirl can be reduced by using these guide vanes, these blades here. So that means we reduce the turbulences, and by this we reduce the total velocity of the airstream, and this increases against the static pressure, and by this we can increase the efficiency of the fan. This is, by the way, the so-called principle of Bernoulli, static pressure, dynamic pressure. If you compare directly the air performance curves of a traditional or standard axial fan, like shown with this brown curve, and the efficiency or the air performance curve of the AxiEco, firstly, we have much higher air performance based on the same motor, both fans. In that case, in that example, we are looking at the fan with a diameter of 300 mil, based on an AC 4-pole motor. In both cases, the same motor, but with the AxiEco, much more air performance. That means we have a wider operating range with a new technology. We have more pressure reserve. For example, when it comes to ice buildup on a cool evaporator. And furthermore, and most importantly, we have a much higher efficiency curve of the AxiEco compared to the standard axial fan. Also noise-wise, this is the same comparison, just a little bit different colors. We have the conventional axial fan, the blue curve. We have the AxiEco as a green curve. Here is the noise. And although we have a higher air performance, we have lower noise with the new technology. So I need to come to the end of my presentation because time is up. Extended system means we have also to look at the energy lost we bring into the system with the fan, because energy lost means heat dissipation, and with a cooling system, bring in heat dissipation means additional load to the system. And if you manage to reduce the loss of the fan, you reduce the heat dissipation which goes into the system. And by this, you improve the total efficiency of the total system. That's the idea behind. Also, subject to do with throw distance, where we have much more throw distance with the new technology. Oh, sorry for this. Yeah. So you see, all these kind of improvements lead to an improved total efficiency of the total system. It's not only the fan, it's the efficiency of the total system at the end. And as I said at the beginning, improving efficiency means also improving the noise, reducing the noise level. Okay, thank you very much for your attention. If you have any questions, please come to our stand, to our booth. We are in hall 4A, and we can discuss further if you like. Thank you very much.